The final part is all about regions in the complex plane. So we've looked at loci, and now we're going to look at how to shade in certain regions. So for this first locus of points, we want all the complex numbers z that satisfy this condition. You can see that it's almost like the loci where you've got a circle or points a distance of 2 away from a particular point. But here, instead of equals 2, we've got less than or equal to 2. So let's try and work out what the significance of that is. And we'll think about it geometrically. So the first thing that we do, just like always, if we're thinking about the problem geometrically, is inside the modulus symbol, we write it as z minus some complex number is less than or equal to 2. So inside the bracket, we're going to have 4 plus 2i. So remember that the modulus of one complex number subtract another complex number is the distance between those two complex numbers. So what this means really is the distance between z and 4 plus 2i is less than or equal to 2. And remember, that's because this inside the modulus symbol, we've got the vector. We can think about it as the vector that starts at 4 plus 2i and goes to z. And when we do the modulus of that vector, we want the length of that vector to be less than or equal to 2. So we want all the points z that are a distance of less than or equal to 2 away from this point here. So if we plot this point here with real part 4 and imaginary part 2, then we know that we want all the points that are inside or on the circumference of a circle of radius 2 around that point. So if we draw a circle of radius 2, it's going to have to touch the real axis, make sure it does. And it can be on the circumference of this circle because we've got a not strict inequality. The distance could be equal to 2, and then it would be on the circle. Because if we just had equals to 2, then we would just draw the circle. So we're going to shade the inside of this circle. If the inequality was the other way around and it said the distance is greater than 2, then we would have to draw shade in the outside of the circle. And just like you would do with the normal shading a region with an inequality, if it was a dashed circumference of the circle, it would mean that the z can't lie on the outside of that circle. So let's just check that that makes sense. If we take any point within this region, the vector, or we're going to think about this as inside the modulus symbol, we've got the vector that starts at 4 plus 2i and goes to z. So we'd have this red vector here. And when we take the modulus of that vector, we're saying the length of that vector. Well, the length of that vector is going to be less than 2 as long as we're inside the circle. So that confirms that the shaded region is correct. So next we've got this inequality. Remember, if we had an equal sign in the middle, this would be a line and it would be a perpendicular bisector. So what we've got here on the left hand side is the distance between z and the point 4 is less than the distance between z and 6. So basically what we want is we want all the points z that are closer to 4 than they are to 6. We want the distance to 4 to be smaller than the distance to 6, so it has to be closer to 4. So if we draw out this Argand diagram and we plot these 2 points, 4 and 6, so both of them just happen to be on the real axis, and that's just to make the example simpler. So these are the two complex numbers 4 and 6. The points that are the same distance from 4 and 6 would be the perpendicular bisector. Okay, I'm going to draw it dotted for now. And if we had this modulus equals this modulus, then we would just draw a solid line down the middle of these two, and that would ensure that the distance to 4 is the same as the distance to 6. Well, we don't actually want to be on that line, we want to be closer to 4. So you can see that these points to the left of this dashed line are going to be closer to 4 than they are to 6. And I've deliberately done that line dotted, and that's because we don't have an inequality here. we want the distance to be less to 4 than it is to 6. And on this line, it would be equal to. So if we did happen to have less than or equal to, then we'd make the line solid, but we've not got that, so we'll do a dashed line. I just wanted to quickly show you, because this is quite a simple example, a slightly more complicated example. Let's say greater than or equal to, actually. So this time we're going to have to write inside the modulus symbol, we're always going to write it as z minus some complex number, and we're going to do the same inside the modulus on the right hand side. And then inside the bracket we're going to need minus 3 and plus 2i, and in this bracket we're going to need plus 4 and plus 5i. So this says the distance between z and this complex number here is greater than or equal to the distance between z and this complex number here. So if we sketch out the Argand diagram, the first thing that we're going to do is we're going to plot these 2 points. So we've got minus 3 plus 2i. That's our point there. And we've got 4 plus 5i. And that's our point there. So we want the points that are further away from minus 3 plus 2i than they are of 4 plus 5i. So the first thing that we're going to do with any of these problems is we're going to put in a perpendicular bisector of the line segment between those 2 points. So if we put a dashed line between those 2 points and then draw in the perpendicular bisector. So I don't know what it's going to look like, something like that. And obviously you can draw it more accurately because you can actually work out what the equation of the perpendicular bisector is. So anywhere on this line, if z was anywhere on this line, it would be the same distance between the 2 points. It would be equidistant. We want the distance from z to 4 plus 5i to be less than the distance to minus 3 plus 2i. So we want all the points that are closer to 4 plus 5i, which are the points on this side of the line this time. Okay? And obviously you could work out the equation of this perpendicular bisector fairly easily. The last one is perhaps the hardest to get your head around. So the first thing that we're going to do is inside the argument, we're going to simplify this complex number or rewrite it as z minus some complex number like we always do. So we've got 2 plus 2i inside the bracket. And we're doing that just like we always do, because now we can think about this as the vector that starts at 2 plus 2i and goes to z. So let's plot this point 2 plus 2i in the Argand diagram. So let's put it there. Okay, so we've got to work out where does z need to be to ensure that the vector that goes from 2 plus 2i to z makes an angle of between 0 and pi over 4 when measured from the positive real direction, so directly to the right of that point. So you can see that z is going to have to be in between this line and the line that moves off at an angle of pi over 4. So if that is an angle of pi over 4, then z could be anywhere in between those 2 lines. Let's just check that that makes sense. And let's imagine z was over here. Then z minus 2 plus 2i is the vector that starts at 2 plus 2i and goes to z. Now the argument of that vector is going to be that angle there. And because that angle is between the 0 angle line and the pi over 4 angle line, then that angle is going to be in between them, so it would satisfy that inequality. Let's just look at another example to make sure you've got that. So here we've got a slightly more complicated question, but it's exactly the same. All we've got is we've got a negative angle here. So the first thing that we're going to do, just like we always do, is we're going to write z minus some complex number inside the argument. So we've got minus 3 and plus 5i like that. So we can draw the Argand diagram, and we need to plot that complex number minus 3 plus 5i. So we're going to draw in a line which moves off at an angle or an argument of minus pi over 6. So minus pi over 6 would be down there. And remember, this is the line that we're measuring our angle from. So that angle there is going to be pi over 6. And it's minus pi over 6, we've moved in the clockwise direction. And z can be anywhere on that line because it's a not strict inequality, it can be equal to. And we also need to draw on the line that moves away from this point at an angle of plus 2 pi over 3. So that's going to be something like, and I've not drawn it very well, something like that. Obviously they wouldn't lie in a straight line. So that angle there is 2 pi over 3. And then z could lie anywhere in this region between these two angles. That's because if we take z anywhere in this region, say down here, then the vector that starts at minus 3 plus 5i and goes to z will have an argument of between minus pi over 6 and 2 pi over 3. So in the final part of this example, you've got to shade in the region which satisfies all of these inequalities. Remember, this symbol here means and. So we want this set of points, and it also has to be in this set of points, and it also has to be in this set of points. So we want the intersection of these three regions that we drew. So we know that it needs to be inside the circle, which is centered at 4, 2 and has radius 2. Okay, so let's draw that circle to start with. We also know that it needs to be to the left of the line x equals 5, because that was our second region. So let's draw on that line x equals 5. Let's put in that as a dotted line, because that was a dotted line, it can't be on that line. So we know inside the circle, to the left of that dotted line, and also it needs to be in between these two half lines, which move off from the point 2, 2. So let's sketch the point 2, 2 on our diagram. Now we've got to be a little bit careful. This is going to be on the circumference of the circle, because this circle is centered on 4, 2. So if we move left by 2, we'd get the point 2, 2, which is going to be on the outside of that circle. And it has to be in between the line that moves off at an angle of 0 and the line that moves off at an angle of pi over 4. So we can label that as pi over 4. So those points that are inside the circle to the left of that dotted line and in between these two half lines are going to be these points, which I'm shading in red here.